time here. And we are live on YouTube as well. So welcome you all who are listening. We will give you 1 minute to let some more connect to our webinar today. Well, since I'm saying the least important things here, I think I will start. Let's see here if I can. Yeah. So welcome to all to this webinar in the FibRe and Treesearch online seminar series. This is a series that we arranged together with the Competence Center FibRe and the research platform Treesearch that is on collaboration for new materials from forest raw material. So we are welcoming you both here on Zoom and you who are following us on YouTube. You can ask questions to today's speaker, Denis Rodrigue from Quebec, Université Laval. And you will have the opportunity to ask questions after his presentation. You who are here in Zoom, you can use the Q&A function, and you who are following on YouTube, please use the live chat function. So I will leave the word to the director of FibRe, Professor Annette Larsson, to give some more introduction to the speaker.
Thank you, Josephine. It's a great pleasure for us to have Professor Denis Rodrigue here today. As far as I have understood, you obtained your bachelor in '91 and your PhD in chemical engineering from the University of Starbuck in Canada, with a specialization on non-Newtonian fluid dynamics. In '96, you moved to Université Laval in Quebec City, where you is now a full professor. Since then, you have been visiting a lot of different places, and to just mention a few, you have been in Mexico, University of Guadalajara. That maybe is wrong, but you can correct me then. And then it was a Technical University of Karlsruhe. And you've also been in Spain and in China, in University of Arts and Science in Rouen, and also in Poland and in France. And yeah, you mentioned there are a lot of places we have been visiting. So you are a very well-known professor in this area. And your main research areas are in characterization and modeling of morphology, mechanical and thermal and rheology properties of polymers and composites, based on thermoplastics and elastomers. So your focus is also covering polymer recycling and rheology. In addition to that, you are also co-editor for 2 international journals, Current Applied Polymer Science and Cellular Plastics, and also in the editorial boards for Applied Science, Cellular Polymers and Elastomers. So it will be a great pleasure for us to listen to your presentation. So I give you the floor to you and look forward to hear your presentation.
All right, so thank you very much for the introduction. I hope that everybody can see my screen now. Yes?
Yep. Yes, but you could go into presentation mode maybe.
Yes. All right, so this morning or this afternoon for you, actually, we will be talking a little bit about how we can improve, let's say, the properties of natural fibers, thermoplastic composites in general, by doing some modification on the surface of the fibers using some specific methods. So the outline of my presentation is I will start with a short introduction, then we'll talk about fiber surface treatment, and I will present two case studies. Due to time limitation, I have to select, let's say, the most interesting one at the moment, and we will finish with some conclusion in general. Just to make a small overview of our research here, we are part of 4 groups or 4 research centers in general. The first one is CERMA, which is the Research Center on Advanced Material. CQMF is the Quebec Center on Functional Material. CREPEC is the Research Center on Polymer and Composites. And we have the CRMR, which is the Research Center on Renewable Materials. So all of these research centers have different objectives, more on the, let's say, experimental side or more on the industrial side, but all of them include materials in general. And in our case, it's mostly a polymer-based material that we are looking for. So these are some of the typical applications that we are working on, depending, is it for automotive, buildings and construction, etc., etc. So we play with the formulation, we do a lot of processing, we do also some characterization on these materials. And at the end, we try to do some modeling based on all the data that we have available for these materials. So again, depending on the type of matrix and the type of fibers that you're using, you will get some different properties. And one of them that I want to focus also is not only on the mechanical properties, but also on the general aspects of the material. So about the quality or the aesthetics of the parts, depending on the application that you are looking for. So these are some of these structures that we are working on as typical examples. So as you probably know, there's a lot of development on the composite side to be able to improve mostly mechanical properties. But now people are more looking into the bio-based material to, let's say, reduce the carbon footprint and have more, let's say, sustainability in the material, depending on the application that you are looking for. So most of the bio-based material that we are looking for is coming from renewable resources. And again, the idea is to use some residues of some of these industries to be able to, let's say, develop some materials that will be, let's say, lightweight and low cost, and try to improve on the properties. Like I said, not only the mechanical properties, but general properties overall. So as you probably know, when we work, let's say, in a composite, there are several problems that we have to overcome. And the most important one here is the fiber matrix adhesion, depending on the type of matrix and the type of fiber that you use into your material. And in our case, most of the fibers are hydrophilic and the polymers are hydrophobic. So there's some incompatibility that we need to overcome in this case. But also, not only on the adhesion, we have to discuss about the dispersion of the fiber into the matrix. And again, we have to talk about the wetting of the fibers to be sure that there will be, again, let's say, good properties overall. So most of these drawbacks are a good limitation, let's say, to be able to get the full potential of these compounds and to achieve, let's say, high performance. So most of the people, what they will be doing is to try to improve most of the time the adhesion between the fiber and the matrix. And one possibility, there's plenty of them, but I will not have time to discuss them today, is to improve the fiber surface adhesion to the matrix by doing a surface modification of the fiber itself. So like we said before, most of the fibers are hydrophilic and the polymers are hydrophobic. So there is low compatibility between those two materials. So one of the big, let's say, solution that we have today is to use some kind of coupling agent, so functional polymers that will have, let's say, a kind of interlink between the matrix and the fibers themselves. And today, since most people are working with, let's say, polyethylene as the matrix, we use maleiated polyethylene as the coupling agent, because there will be, let's say, an esterification reaction between the maleic anhydride that you are grafted on your polyethylene that will react with the hydroxyl groups on your, let's say, cellulose fiber or natural fibers in general, and the polyethylene, let's say, chain on your matrix will entangle with this this coupling agent. So there's a kind of a bridge that can be built between the fiber and the matrix in this case. And most of the time, the people will just blend this coupling agent inside of their compound when they use, let's say, an extrusion system or a melt internal mixer, etc., etc. But this system is work fine, but it's not optimum, because you can imagine that not all the coupling agent that you had into your mixture will go actually at the interface between the fiber and the matrix, and you will lose some of these molecules that are quite expensive compared to the polymer and the matrix, polymer matrix and the fibers that you're using in this case. So we try to find ways to improve the efficiency of these coupling agents to be able, let's say, to reduce the cost and have better mechanical properties at the end. So one of the development that we have proposed in the past, and we are still working on that, is to do some kind of solution treatment on the fibers themselves. So most of the people in the past use mercerization as a surface treatment of the fibers. And this step is mostly to clean out the fibers from the impurities and all the components that you have on their surface. And the main idea in this case is to expose as much as possible all the reactive groups that you have on your fibers, which are the hydroxyl group in this case. So once you have done that, you have a clean fiber that is available now to be able to modify on the surface. And we graft directly the maleic anhydride, let's say, polymer on the surface by dissolving in, let's say, making a solution of your coupling agent inside a solvent. So you have to select the solvent that will be able to dissolve actually your coupling agent that you're using. MAPE is quite difficult because we have to use with specific solvent like xylene or TCB at high temperature. Then you optimize the fiber solution ratio. You do your mixing for specific time. You filter the material, you dry, you clean, and then you have your fibers that have been treated with the maleic anhydride, let's say, polymer specifically on the surface of the fibers themselves. So the first thing that you have to do is to be able to confirm that you have a surface modification of the fiber. The first thing to do is you can actually look at FTIR in this case. So you see here that the red curve is related to the treated fiber and the black one to the untreated fiber. In this case, we use maple because we have a lot of maple in Canada, but you see here that there's a lot of CH2 and CH3 that are now on the surface of your fiber. This is coming from the PE part of your, the PE part of your MAPE. And actually, if you look at around 3,300 here, which is the hydroxyl group, the red curve has a lower intensity. So you have covered some of these with your coupling agent. So that's one way that you can use to see that there is a coupling agent on the surface of the fiber. The other way that we do it also is to use TGA. So by using these curves, you see here that there is some slight differences between the treated in red and the untreated in black, especially at around between 400 and 500 degrees Celsius, where you see this peak in the derivative here, which is related to the MAPE that you have on the surface of your fiber, which is not there on the untreated fiber. So these two methods are usually enough to see that you have actually something on the surface. And then we go for typical processing of the material. So most of the people, what they do is they use their wood, and they use their polymer and some kind of additives like lubricant or coupling agent. You have to dry the wood before going into an extruder. Then you produce your pellets, you dry again. Maybe you have to grind the material, and then you dry again. Now you have to mold depending on which polymer you are using, and again, which system you want to use to produce your part. So in our case, what we propose is you use your wood, treated or not, in solution, then you mix with your polymer. That can be actually done in a dry blend system. So you have your powder of wood and you have your powder of polymer. Then you go directly into a molding system and you have a direct part that can be produced. So you reduce, in this case, the number of steps into your system. And this is very interesting in terms of industrial scale up when you want to produce good parts based on these wood plastics composite. So one of the applications that we, let's say, develop a lot here in Quebec is about rotational molding. So in rotational molding, you can start with the material in a powder form, then you put that into a mold. The mold goes into an oven where you have biaxialization that is imposed on the mold itself. So you have the material that is melting and distributed into the mold itself. And the idea in this case is to be able to produce a part that can be relatively big, but also an empty part. So something that will be just a kind of shell. But the main advantage of rotational molding is you don't have any weld line because the part is molded in a single step. And the welding lines are usually weak points, especially when you have composites due to the weld lines. So again, this is a big advantage in this case because you start with the material in a powder form and you can directly have your part without any, let's say, modification to do. So here you see on the left the part that we have produced by rotational molding using the neat polymer. In the middle here, you have untreated wood. And when you look at the treated wood, you can clearly see that the surface quality is much better. You have better fiber distribution, and there is, let's say, better quality and aesthetics of the part in itself. So that's a big advantage of having the fibers before treated before you include that into your mold to produce the part in this case. So that's one big advantage. So if we look, let's say, at different parts here, we are playing now with different types of fibers. So we use hemp, rice husk, hardwood like maple, softwood like pine. We use flax, so different types of lignocellulosic material that is available. And we have a lot of students coming from different places. They bring their own fiber. We do their processing and characterization, and then they go back with their results and finalize their thesis. So this is usually what we do in terms of collaboration with a lot of universities, I would say, around the world. So we also use, let's say, bio-based material as the matrix itself. So this is a part that we have produced using rice husk with the PLA, polylactic acid. So that's a full bio-based material. And this is very interesting in terms of sustainable development in this case, depending again on the final application that you are looking for. So another, let's say, development that we are doing is to produce what we call hybrid systems. So in hybrid system, we use two types of reinforcement of particles into the system. So the maple fibers here are used to impose, let's say, more strength, more rigidity into the material. But the problem with these systems, most of the time in composite, is you lose a lot of ductility. So what we have done in this case is we have added the GTR, which is ground tire rubber, so another residue, another recycled material, to impart a little bit more elasticity, a little bit more impact strength in the material. And by combining these two particles, now you can adjust actually the mechanical properties between, again, rigidity from the maple fibers and the ductility coming from the rubber particles. But again, all this material can be of recycled origin, so you can produce actually good parts using a very low-cost material. If we look at the mechanical properties, I just presented here, let's say flexural modulus on the left and the tensile strength on the right, which are the two main properties that we are looking for these materials. So if we look on the left, you can see that compared to the neat polymer matrix, which is the red line here, so the black curve or the black data here are for untreated fiber. So you can actually increase, especially when you are in that 15 to 20% weight percent. But if you go with the treated fiber, which are the blue lines here, you manage not only to get better properties, but you can add more fibers up to 30% in this case, which is very interesting to do. So not only you have better mechanical properties, but you can actually add more fibers because they're more dispersed and have better contact with the matrix. If we look at the tensile strength, that's usually the case with the polymer composite, where you have poor compatibility between the matrix and the reinforcements. So the value is going down when you increase the fiber content for untreated fiber. But when you use treated fiber, actually the curve is going up. So again, this is something that is of interest and showing that you have good coupling between the matrix and the reinforcement in this case with these increasing curve, especially up to 30% in our case. So that was the first part of the study that we have done. So the idea was to surface treat the, let's say, fibers using a coupling agent that we put directly on the fiber. So we went a little bit further and said, okay, if we have to put the fiber in a specific matrix, instead of having a coupling agent, why not graft directly the polymer matrix on the fiber itself? So this is actually easy to do when you have, let's say, polyolefins like polyethylene or polypropylene. And this is what we call polymerization compounding in this case. So the idea is on the surface of your lignocellulosic fiber, you have a lot of hydroxyl groups that are available because we actually started with mercerization. We clean the surface of the fiber. And actually what we do is we chemically anchor the polymer on top of the fiber itself. So the OH groups are actually used to fix a catalyst and a co-catalyst. So in terms of polyethylene, you use a TiCl4 and ElCH2H53, so triethyl aluminum. So by using this catalyst, co-catalyst anchored on the surface of the fiber itself, then you can directly polymerize your polyethylene on the fiber, and now you have a good, let's say, interaction between the fiber and the matrix because it's chemically anchored on the surface. So in this case, the fibers are actually playing two roles. First, they are the site for the chemical reaction when you polymerize your polyethylene in this case. And actually at the end, everything is left in the system and the fibers are acting as reinforcement when you blend that with a matrix, which is polyethylene that was selected in this case. So there is a lot of information on this type of catalytic polymerization in the literature for inorganic material, but there is not much on organic fibers like lignocellulosic material. So in this case, we wanted to use this technique on different fibers. In this case, I will present the result on hemp, but actually it can be applied on any kind of system. And we use a linear medium density polyethylene as the matrix because we wanted to have a good balance between strength and elasticity for the material. And in particular, what we wanted to do is to make some characterization of the material, not only in the solid state, because we want to improve the mechanical properties also, but we wanted also to do some characterization in the melt state for two things. The first one is to see how the material will behave when it will be processed, so mostly in the melt state, and again to see if standard rheological technique can be useful to detect again this surface modification of the fibers depending on the type of grafting that you're using. So in this case, it's quite easy. You start with the mercerization. So you put your fibers in the NaOH solution at room temperature. Then you dry the material overnight. So you have your pre-treated fibers. Then you go into the polymerization step. So we actually use hexane in this case to be able to polymerize polyethylene by adding the catalyst and the co-catalyst in this case. And after that, you just add your monomer. So you bubble actually ethylene into your reactive system, and you get your polymerized polyethylene on top of the hemp or the fibers. Then you dry the material and you're ready to do some composite processing in general. So you recover the fibers, but the fibers are actually surface treated with the matrix that you want to use at the later stage. So you put your two materials, so the fiber and your matrix, into extrusion. Then you pelletize the material. In this case, we use injection molding to prepare the sample. Then you cut your sample, and you will be able to do some characterization directly on them. So in the results, I will present the codes like this. When you see L and H is related to the unmodified fiber, and when you see LPH, which is the modified fiber related to the polymer that was grafting on the system. And again, the first thing that you need to do is to be able to determine if the fiber surface modification was successful. And after that, you will be able to see what mechanical or rheological properties you can use to see the modification is efficient or not. So again, seeing is believing. So on the left side here, you see the fibers that was mercerized, so very clean and smooth surface because you extracted all the residues and all the impurities on the surface of the fiber. But on the right side, you see that there is a lot of structure that is on the surface of the modified fiber, which is related to the amount of polyethylene, the molecules that you actually grafted on the surface of the fiber. So this is how we managed to actually see this modification. And again, we did the TGA to confirm and to be able to quantify the amount of polyethylene that you actually fixed on the matrix. And again, you see between 400 and 500 degrees Celsius, there's a small bump which is related to the polyethylene itself. So the neat polyethylene is in red. So you see that it fits with the range of temperature that we're looking for. And by doing some calculation, we saw that most of the time we have actually 20% by weight grafting degree of polyethylene on the surface of the matrix, which is quite good to recover the surface and have good properties with the matrix. So again, here we see some standard SEM images on the left without surface modification. So you see a lot of holes and fibers that were pulled out when you do these types of analysis. And on the right side, you see a very smooth surface and let's say less defect into the system, because now you have better compatibility with the treated fiber and the matrix. So that should give you, let's say, bigger mechanical properties at the end. So the first thing that we did is a standard rheological analysis in the melt state. So using a small amplitude oscillatory shear. So here you see in red, you have the neat polyethylene. In green, you have with the untreated fiber. And in blue, you have the treated fiber. So again, much higher viscosity related to the better interaction between the molecules and the matrix. So in this case, you have, let's say, more flow resistance, but you have better interaction between the matrix. And one way to characterize that is to use the modified equation for the viscosity itself. So we use the modified cross model in this case. And when you look at the parameters, you see that there is a significant increase in the yield stress and also a significant increase in the zero shear viscosity in the intermediate plateau. So again, this proves that there is significant difference between the untreated and treated fiber, and that can be quantified just by using a simple rheological analysis at a small deformation. We did also types of characterization. So this is typical here, Van Gogh-Polman plot. Again, all the characterization was done at the processing temperature of 180 degrees Celsius. And what is more important in this case is that you see that the maximum of the curve here occurs at a higher modulus. That means you need more stress to be able to deform the system. So this is related again to the good coupling that you have between the matrix and the fiber. Another thing that we are looking for is about the activation energy. So all the properties are changing with temperature. We saw in this case that, again, due to the better coupling, the activation energy was much higher with the treated fiber. So again, this proves again that you have some good modification at the interface. So I will go fast on these the other results because they're all giving the same information. So you can do actually DMA, so some kind of rheological analysis, but in the solid state. And we saw that the transition temperature was shifting and the height of the value also was modified due to the presence of the fiber and the surface modification in this case. So we do a lot of other characterization like creep strain. So again, more time dependent properties to see the difference again between the blue curve, the green curve, which is the untreated fiber, and the red curve, which is the treated fiber in this case. So what we have seen here, it was mostly modifying the characteristic time of the system. Again, you have more resistance when you have the treated fiber. And we did also some relaxation experiments in this case, when again, you see some clear modification between the treated and untreated fiber here in the green and the red curve here. And again, there was some big difference between the recoverable and the viscoelastic deformation of the material related to the coupling agent that we have at the interface. And again, another type of transient step is here that is related to another type of characterization that we do. And with all these curves, we're able to fit some standard models to be able to quantify the difference. And you can see that there be some significant difference between the treated and the untreated fiber in terms of viscosity and characteristic times, et cetera, et cetera. So rheology is very important to characterize the effect of the interface, because actually the contribution of the matrix compared to the solid state is less important. So at the end, how it goes with the mechanical property. So you look at the tensile modulus. So there was some significant difference and increase by adding the modified fibers. We look at the tensile strength. So in this case, it was a very big difference from 14 to 20 MPa in this case. But what was more important is that the elongation at break also was quite high. So in this case, it's very interesting to see that we are able to get good modulus, strength, and elongation at break, to a good combination of all these properties just by having these surface modification on the fiber itself. So as a short conclusion, I think that everybody knows that lignocellulosic fibers are used with different applications today. Let's say for polymer composite, we're working on other types of matrices also here, but this is my main research area here. And it depends on the final application that you're looking for. But in most of these cases, the fiber surface modification is the best or the most efficient ways to have better properties at the end. Like I say, not only mechanical properties, we can look at other properties, but it would be similar. But there is, let's say, a high potential to develop other type of matrices and also a complex structure. And this is actually what we are doing in our case. So hybrid system, how you can blend different types of reinforcement. Foam system, so try to reduce the weight. Sandwich system with different layers, again, to maximize the strength over weight ratio. And one of the big, let's say, area that we're working on right now is about density graded material. So with the fixed amount of reinforcement, if you distribute that, let's say, differently into your material, how you can improve, again, the mechanical properties of your systems. So this is something that is of interest for, let's say, again, maximizing the properties and reducing the cost and the weight. So I thank you very much for your attention, and I will be able to answer some of these questions today. So thank you very much.
So thank you. We are opening up for questions, and we have any. And you who are here in Zoom, please use the Q&A function. And you who are on YouTube, please use the live chat function.
Josephine, we have one in chat, but I also have some questions if you. So should we start with the one in the chat?
And let's take your question first.
Okay. Thank you for a very nice presentation. It was super interesting. I really liked it a lot. And I have a lot of questions, but I can't keep you forever. But you said that I think it was in slide 25, you had modified the surface of the fibers, and then you had. Did I understand you correctly that you had got about 20% of polyethylene on the fibers?
Yes, this is what we do mostly by doing the TGA. So we calculate the weight loss of the untreated fiber, then we calculate the weight loss of the treated fiber, and the difference is actually related to the amount of polymer because it's not degraded at the same temperature as the fiber itself. So most of the time when you change the conditions here, you manage to have more or less, but again, it's always an optimization because you need to recover the full surface of the, let's say the fiber itself, but it depends on the thickness of the layer that you produce.
Mm. And later you were testing them in different ways, for example, rheology. Yes. Did you add more polyethylene to that system, or was it just the one that was on the surface?
Yes, that's a good question.
Just the one that was...
Yeah, we tried to mold the fibers directly, but it was not very good. So what we have done in this case is we actually use the treated fiber at different concentration in the polyethylene matrix, and we calculated back the real fiber concentration depending on the amount of polymer that we added and the polymer that was already grafted on the fiber.
Okay, so without adding any more polyethylene, it was very difficult for you to process it. Was that valid for all different thermal processing techniques? Or could it have been compression molding for molding? Should that have worked?
Yes, it was actually borderline a little bit. We were able to produce some parts, but it was not very good actually. So again, it depends on the application that you're looking for.
So do you think the 80% of bio-based materials is the upper limit?
We did a little bit more, I would say up to 85, 90. It depends on the surface treatment and the type of matrix also.
Okay, thank you. Thank you for a very interesting speak. And I give back to Josephine.
Yes, we have a quite long question from Lucas Kneisel. So maybe, Lucas, you want to say the question yourself, if that's okay, if you can just type something in the chat that I can give it the word to you. Okay, we will leave the word to Lucas. Find you here in there. Now you're...
Yeah, hi. Thank you very much for that talk. It was really interesting. I would have a question mainly related to the processing technique that you showed in the beginning with the rotational molding. I guess the main limiting factor for like the selection of materials is the melt viscosity of the polymer.
Yes.
Is there like a possibility to for example, because I guess the biggest, like in both directions, too thin of a viscosity and too thick is both a problem. But like are the shearing forces high enough that, like, for example, shear thinning fillers would already like come into play or would work already at these speeds and these forces that act in the mold?
That's actually one of the biggest advantage of rotational molding. Is contrary to most people think, the velocity of the rotational speed is quite low. We're working about 2 to 4 RPM, so there's actually no shear on the material itself. So the idea is to have something that is in a powder form that will be able to flow or to move around the mold. When you heat the mold, the materials start to melt, and then you recover the inside part of your let's say of your mold. And the idea is you can have actually complex geometry like the one that is showing here that you can produce in a single step. So when you talk about the viscosity of the material, yes, there are some limitations. Most of the people try to have a melt index around 4, 6. But again, melt index is not really a good indicator because you're actually looking at the zero shear viscosity of your material. But for the matrix itself, I'd say we have worked with polyethylene, polypropylene, nylon, PLA. Actually, there's a lot of different, let's say, polymers that can be used as the matrix. But the main parameter, again, would be the molecular weight because this will control the zero shear viscosity. So you need high viscosity enough to be able to, let's say, have the material stick to the walls and stay there, but you need, let's say, low viscosity because you want all the interparticle voids to be, let's say, moved out before you have a part that will be demolded. So you have to remove all these voids.
Thanks. Just one quick thing. Could this also be like put further towards like also a solvent-based system rather than a melt-based system that you just evaporate your solvent during the rotational part, or go even like one step further to some kind of like a reaction rotation molding where you use?
Yeah, I think it has been done in the past. Actually, rotational molding started with liquid resins at the beginning because it was easier to mold, and like you said, it can be reactive or not. Again, it's a question of controlling the time and the temperature of your system. That then again, that can be done quite easily into your into a processing system. So yes, it is possible. Again, the problem with the solvent is you need something that will be cheap because you lose it every time.
Thanks.
And then we have questions from Professor Eva Malmström, who I think I will allow you to talk, Eva. So you ask the question directly.
Yes, just finding the right button. Thank you very much for a fantastic, inspiring presentation. I'm really curious about your results for your grafted, when you graft polymers on the substrates. Do you think that it's critical that the polymer is actually covalently bonded, or would it work to have a polymer physisorb to the surface instead, or a latex that sort of preferentially goes to the surface?
I think it's possible to do it like you said. Again, the idea is to be able to try all the possibilities and the combination, but I think it should work. Again, it's just to find the right condition to be able to do this reaction in a specific test. Because in our case, we started with polyethylene. It's quite easy, and it's one of the most, let's say, used polymer that you can find at least data in the literature, but it can be done, let's say, using other monomer or other polymer. You just have to adjust again the catalyst and the conditions, etc. It can be done. If you have, let's say, the surface reactive groups on your fibers, no problem.
Thank you very much. Thank you.
Thanks.
Okay, and we from YouTube, we only had one comment, and that's a great presentation from Olle Andersson. So I think we again say thank you for the great presentation. Very interesting. And this was the last webinar for the spring term. But sure, we will be back again, Annette? Or...
Absolutely, absolutely. We will come back in the autumn with the dates and so. We will have at least 2 presentations.
So please go to the treesearch.se to find more information and keep yourself updated, or follow us on LinkedIn or on YouTube. So thank you all who've been listening. I forgot to say that before, but thank you so much.
Thank you very much.
Thank you, Dennis. Thank you.
Thank you.
Really nice presentation. I was also